For today's lesson, we are going to begin Chapter 3 of our book. And so Chapter 3 concerns itself with the various methods of proving results in mathematics. We will also be skipping to Chapter 6 so that we can cover mathematical induction next week, and then jumping back to 3. But that's the goal for the next week, is going through the various ideas that we have when it comes to proving. Today specifically, we will be looking at direct proofs, and so those are proofs of the form P implies Q, and we will also be looking at the contrapositive. And so recall that if we have P implies Q, then that is logically equivalent to not Q implies not P. But before we get there, I'm going to do something different than what I have done in the previous videos. And this is part of what I will be doing throughout the term, about once a week. I am going to give you a preview of another course in our course offering that you can take having taken structures. And so specifically, I want to build off the example we finished off last time and talk about what are open sets. So for example, in calculus, we look at these intervals. So as a reminder, at the end of our last lesson, we let I be the indexing set, which we took to be the positive integers. And then we took j to be an I, so simply j is some positive integer. And we looked at the collection of sets, negative 1 over j, comma 1 over j, where here x is a real number, and we have that x is in between these two values, but it is not equal to negative 1 over j or 1 over j. And we argued through intuition that if we took the intersection of all these sets, that we just get back 0. And if we took the union of all of them, we would just get back negative 1, comma 1, because a2 is contained in a1, where now I'm looking over here. So we have our a sub 1 set, that's negative 1, comma 1. Then a sub 2 is negative 1 half, comma 1 half. But as we continue, the j's grow larger, so that means that in absolute value, the 1 over j's, negative 1 over j or positive 1 over j, they are going to get smaller and smaller and smaller. And so they're always going to be contained in a1. And so the union of all the sets is going to be simply negative 1, comma 1. Now in calculus, open sets play a big role. When you see the definitions of continuity, the differentiable function, you will see this phrase where you have that the function is continuous or differentiable on some open set U. But we really don't explore what that means further until you take a course on real analysis, which we will also talk about later. And so real analysis does concern itself with how does one prove the statements that you see in Calculus 1 and multivariable calculus. But what I want to do instead is focus on the notion of open sets. In multivariable calculus, you also investigate open sets, although we don't really formally cover them. But one of the things that we sort of do in a hand-wavy way is say that an open set is something that has like no boundary. And so we have like some curve C, and we look at the interior. And so this is what I'm doing with the dotted lines here. So we have some space curve C in the plane, and we have that we'll define the open set as everything in the interior, but not including the boundary. And so an example of this would be open disks. So if we look in R2, and we consider the following set U, where this is the collection of points, x comma y, in R2, such that x squared plus y squared is less than 1. This is an example of an open set in the plane. And so now we're looking at the unit disk, centered at the origin of radius 1. But now, of course, we are not including the boundary. And so that's an example of an open set. But how does one formally define open sets? Because it is a notion that you'll see in various courses, but what are they? And so this is a question that mathematicians asked in the late 1800s and 1900s, is how do we formally define open sets for a set? In other words, how can we axiomatize them? And this falls in line with the perspective that mathematicians had in the late 1800s, early 1900s, which was to formalize mathematics in the language of set theory. And what they did was consider examples such as these. If we look at open sets in the real line, so if we're just looking at the real numbers, then as we saw in calculus, if we have something like -1, 2, we can take the union of this with 3, 4. We still will not have any boundary points, and so we will have that these things are open. And so mathematicians extrapolated from these examples that if we take a union of arbitrary open intervals, and when I mean open intervals, I mean something with the form like -1, 2, or more generally a, b. If we take arbitrary unions, we will always be getting back an open set. So we can take -1, 2, union 3, 4, union 4, 5, and so if we do, like, say 4, 5 here, this is still going to be open. But now, when we look at the intersection, we have to be careful, because if you take an arbitrary intersection, so here we have an intersection of infinitely many sets, we get back 0, which does not coincide with our notion of what it means to be open in the real line. It cannot be written as an open interval or a union of open intervals. And so this led mathematicians to define what is known as a topological space. So topology is our course Math 354. It only requires math structures as a prerequisite, but it does exactly that. It formalizes this notion of open sets in a complete general construct. So here's the definition of what it means to be a topological space. If we have any set X, and we now take another set, which we're going to denote by T sub X. Now, T sub X is a subset of the power set of X. We say that X, comma, T sub X, so this pair, is a topological space if the following axioms are satisfied. We have that X, the whole set, and the empty set are in T sub X, and we have that the intersection of a finite number of sets in T sub X is also in T sub X. And if we take an arbitrary union, then we have that will also be in T sub X. And we call the elements in T sub X the open sets of the pair X, T sub X, this is the topological space. And so in the notion of the real numbers, we have that the whole space is the real number, so we have -infinity to infinity. That is considered open in the language of topology. We never consider the empty set in calculus. However, we can take an intersection of two sets, like 1, 2, intersect 3, 4, and they have nothing in common. And the key idea here is that we want to make sure that we always land back when we take a finite intersection back in T sub X. And so now the empty set must be in here. And it turns out that this is all that one needs to define the notion of a topological space that agrees with the intuition that one has from the real numbers, from R2, from the complex numbers, and it can now be done in a more general setting. To just put this in context with the notation that we have introduced, we can go ahead and rewrite 2 as follows. We can take some u sub j's in T sub X, where each index j is in some indexing set that is finite. And then if we take the intersection, by construction, I is finite, so this is a finite intersection, then this is back in T sub X. And similarly, for 3, the union of an arbitrary number of sets in T sub X is also in T sub X. We have that u sub j is in T sub X, where now we have that the subscripts, the j's, they're in some arbitrary indexing set I. So this I could now be infinite. And just as before, we now have that the union, as we range over all those j's in the indexing set I of the u sub j's, that is back a now of t sub x. So what we just discussed is what is done in the first couple of lectures in topology. But for the remainder of the course, one of the main questions of study is declassifying topological spaces. When are two topological spaces the same? And what does it mean to be the same? And so one way of thinking about how topological spaces are the same is if we had, say, a ball of Play-Doh. And if we were to mold it into any other object, and so long as we did not break it apart, then those two objects will be considered to be the same. So in a way, a donut is the same, topologically speaking, as a coffee mug. Because if we start off with a donut, we can go ahead and do what is portrayed here on the screen. We're not breaking it, we're just squishing this down, and now all of a sudden we have a coffee mug. And so these are ideas that you can explore further in topology. To begin, I want to make a distinction of the various names we have in mathematics for theorems. Now, Bellman does not make this distinction. He calls everything a theorem, as you will see as you read through his text. A couple of exceptions towards, once we get to chapter 5 and 6, is that he will actually start to use lemma and corollary. However, in mathematics, we do not use the word theorem for every single statement, but reserve it for the important results. Now, proposition is the same word as a theorem, just that it may not necessarily be the main result of the section. And so whenever you see proposition and theorem, the way you want to interpret it is theorem is to highlight this result is important, may probably come back later, whereas proposition, it's something that we can prove, but may not be as important. However, that comes with a level of subjectivity. There are mathematicians that will look at a certain theorem and be like, oh, this is just a proposition, this is not that important, and vice versa. Oh, this proposition should be upgraded to a theorem. And so there is a level of subjectivity. But I want you to be aware of this distinction of theorem versus proposition and the subjectivity of when to use them. And so usually when I do my lectures, I will label things proposition, and then for a result that we will probably use again later, or has a significant historical background, I will label those theorems for those reasons. Now, a lemma is also a theorem, but the thing about a lemma is that it is proven primarily for the purpose of using them to prove a proposition or theorem down the road. And so you can think about lemmas as the mini theorems, the building blocks to prove something else. And finally, we have corollary. And a corollary is a consequence of a theorem, proposition, lemma. And usually these are followed immediately after one does a theorem, proposition, lemma, respectively. We'll just say corollary, and then there'll be implicitly understood that that's a corollary of the previous result that was just proven. And so these are the four different types of theorems that we have, the names that we have for theorems in mathematics. And so we're going to begin our coverage of proofs with looking at P implies Q. And so this is the idea of a direct proof. We want to assume P. So to prove P implies Q, we want to assume P. Then we're going to have an argument that assumes P. And finally, using that argument, we want to be able to conclude Q. And so now, if this is valid, that means if P is true, now we have that then Q will be true via this argument. And so in Bellman, he goes into further detail of the logical aspects of of the building blocks that come in here. But what I want to do instead for our lecture is do as many proofs as we can into this video, and then discuss afterwards the logical aspects of how that argument can be translated into the material we covered in the first two sections. And so to start off, let us make a definition. we're going to take some integer a, and we are going to define what it means to be a factor of an integer. And so we say that an integer d is a factor of a if there is some k, some integer k, such that a is equal to d times k. And so now we have that d is a factor of a. We can also say that d divides a. And so I'm just going to write this here. That d divides a. So that's another equivalent way of defining a factor. And so with that, let us go ahead and prove the following proposition. So here we have integers a, b, c, and we have that a is a factor of b, and a is a factor of c. And then we want to prove that a squared is a factor of b times c. And so here we have our if statement. So we have our p is this portion here. So this here is our p. And over here we have our q. A squared is a factor of b times c. And so we want to be able to prove this. And so what we are going to do is assume our p and then use the knowledge that we have to be able to deduce that a squared is in fact a factor of bc. Now, whenever we do prove something that early on it may seem that we can just do these all from the get-go, but it is good to start off with some scratch work and then leave the actual proof writing to the end once you know what the argument that would get you the conclusion is. And so for example, we can go ahead, I'm going to go ahead and write my scratch work in blue. So what are we given? So what are our assumptions? So we know a is a factor of b. And we know by definition that this here is, this is telling us that there is some integer k, oops, I mean to erase, that there is some integer k such that b is equal to a times k. So we have, there exists some integer k such that b is equal to a times k. We also have that a is a factor of c. And so now this tells us that there is some integer, but now we need to be careful. We've already reserved the symbol k for this factor here. If we use k again, it is now unclear which k that refers to. Will we refer to that k here or the k that we're going to use for a times k equals c? And so instead we want to say some other symbol. So let's choose L such that c is equal to a times L. So notice, if I had chosen k here, we would be saying that c is equal to ak, b is equal to a times k, so therefore b must be exactly c. And so we do want to make sure that we change the symbol. Okay, so now we have this. So now if we put these two together, and so what we want, so the goal is to show that b times c is equal to a squared m for some integer m. And so that's just what it means to be for a squared to be a factor of bc. So we want to show this. But that means that what we have to do is multiply b times c. So if we multiply b times c from both equations, we have b times c is equal to ak times al, which is equal to a squared kl. And so now we can take our integer m to just be kl, and we have this. Now, something that I did that I want to emphasize is, earlier on when we talked about biconditionals, I mentioned how every definition is a if and only if. So notice that this statement I wrote as an if. And then over here, this seems like an if then. But because we're using the definition, we actually do have an if and only if. And so we have A as a factor of B, if and only if this is here. And this is just to emphasize what I mentioned out loud in that section. That whenever we read a definition, even though we write if, we really want to keep in mind that it is a if and only if. And so we have our argument. So this shows that A squared is a factor of B times C. So now we can go ahead and formally write this as a proof. And so let's go ahead and do this. So let's go ahead and write down our assumptions. So we're going to go ahead, let A, B, C be integers. If A is a factor of B, then by definition, there is an integer k such that we have that B is equal to A times K. Similarly, if A is a factor of C, then there is some integer L such that C is equal to A times L. Multiplying B times C then yields BC is equal to A squared times KL. So in particular, A squared is a factor of B times C, which concludes the proof. And so now we have a proof for what we have done with the scratch work. Now, when writing a proof, we usually will write this out in English entirely. And so notice that when I did my scratch work, I used a shorthand. So I used there exists K and Z. In practice, when writing a formal proof, we do use symbols, but there are times where, for example, it is preferable to just say it out. Instead of, we can say there exists L and Z, there exists K and Z, but oftentimes we just opt to write everything out in English. And so there is some integer L such that C is equal to A times L. And so we have our proof here. Now, as a corollary of this, we have that if A and B are integers, and P is a prime factor of A and B, then P squared is a factor of A times B. And so this is just to emphasize the use of the word corollary. So notice that this statement is really just a restatement of the proposition, where now what used to be A in the proposition is now our prime P. And we're being told that P is a prime factor of A, and so A is now B. Our old B is now A, and our old C is now B. And so then we have that P squared is a factor of A times B. So it really is a restatement. Now this corollary restricts to the case when we have a prime number as a factor, but the proposition does it in complete generality. So long as we have that A is a factor of both, doesn't matter if it's prime, we will have that its square is a factor of BC. And so just want to emphasize that this is one instance where we can write down a corollary, where now it's just a specialization of what we had just proven. And so in this case, this will not require proof, since it is a restatement of the proposition. So we can just simply say, this is a restatement of the proposition, so the result follows. So let us do another proof. So here we have the product of two integers is odd. So let's restate this. So we can restate this in the following way. So we can say if m and n are odd integers, then m times n is odd. And now we can go ahead, we can start our scratch work. And so here we know that by definition, this is going to be 2k, m is going to, because m is odd, we're going to have that this will be 2k plus 1 for some k in z. We also have that n is equal to 2 times l for some l plus 1. And so if we multiply the two, we will have that m times n is equal to 2k plus 1, 2l plus 1, which is going to be 4k times l plus 2k plus 2l plus 1, which we can then write as 2 times 2kl plus k plus l plus 1. And so now the reason I'm writing it in this way is that now we have our emphasis on the fact that this is 2 times some integer plus 1, which is the definition of what it means to be odd. And so what we did was we put our assumptions, our givens. We were told that m and n are odd integers. We used in our scratch work the definition, and we put this down, and then we can see that yes, this here is odd. But notice, and this is the idea of scratch work, this is something that when you write down, this is your work to yourself, in the sense that you are able to follow it in the moment, but then if someone else were to read it, it may not be as evident what the argument is, since we are condensing a lot of the thoughts that go into it. Whereas in the proof, we want to go ahead and lay all of our ideas down on paper. So for example, if we now go ahead and formally write this, we have, so just writing down the assumption, so suppose that m and n are odd integers. And so notice that in the previous proof and in this one, I am starting off by informing the reader what we are assuming. Yes, this is in here, but we want to then restate it. So we want to inform the reader, this is what we are taking for granted at this very moment, namely m and n are odd integers. Now we know, we apply the definition. So by definition, there exists oops, 1 second. That's right. There are, just to change the, so I used excess earlier, so we can just change things slightly. So there are integers, k and l, such that m is equal to 2k plus 1, and l is equal to, n is equal to 2l plus 1. And so now we have that portion of the scratch work. And now we go ahead and multiply. So hence, m times n is equal to 2k plus 1, 2l plus 1, and we already have the scratch work, so we can go ahead and write that this is the same as 2kl plus k plus l plus 1, which shows that m times n is an odd integer. And we're done. We got the proof. So the next statement we are going to prove is the following exercise from 3.1, namely number 8. And what it says is, if A, B, C, and D are sets, and we suppose that A minus B is a subset of C intersect D, and X is in A, then if X is not in D, then X is in B. And what I am going to do for this proof is to do this via the contrapositive. And so recall that if we have P implies Q, that this is logically equivalent to not Q implies not P. And so this is what we call the contrapositive. Now, in our next video, I will be doing a direct proof of this statement, but we will need a technique via contradictions to do it directly. And so we'll come back and do this proof again in our next lesson. So what is a contrapositive here? Well, here's our P, then Q. And so we want to say X is not in B, then X is in D. So let's do our scratch work. So scratch work here. So we want to do contrapositive. And so we have X is not in B implies X is in D. And so we now let's look at our givens. So we also have that A minus B is contained in C intersect D. We have that X is in A and X is not in B. This is now coming from the contrapositive assumption. So now, these two together, X is in A and X is not in B, that's the definition of of what it means to be an A minus B. So recall that A minus B is the set of elements Y such that Y is in A and Y is not in B. And so in particular we have that this here is telling us that X is in A minus B. But then if X is in A minus B, we have that this here, A minus B, is contained in C intersect D. And so we then have that X is in the intersection of C intersect D, since A minus B is a subset of C intersect D. But then this is saying that X is in C and X is in D. But that's what we want to show. We have X is in D. So we got our desired conclusion. We have that X is in fact in D. So we have enough scratch work to actually now lay out a formal argument for this proof. So let's go ahead and do that. So let us get started with the proof. So we're going to say, so here we have suppose. So we're going to put in our assumption, suppose A minus B is a subset of C intersect D. So here you can say A, B, C, D are sets. And in this case, it is fine to not say that they're sets since it is part of the assumption. And so we can just say A minus B is a subset of C intersect D. And it's optional to say where A, B, C, and D are sets. And so here and X is in A. And so that's our first assumptions. And now what we want to do is inform the reader that we are going to do the contrapositive. And so we will show the proposition by proving the contrapositive. So suppose that x is not in B, it suffices to show that x is in D. And so now we have explained that we are going to be doing the contrapositive. We are given the first assumption and what we need to conclude. Alternatively, you can say that you're going to show the proposition by proving the contrapositive, colon, and then saying, if x is not in B, then x is in D. And so you can then rewrite that. So those are perfectly valid. So now we go through our arguments. And so we can go ahead and say, since x is in A and x is not in B, we have that x is in A minus B. Since A minus B is a subset of C intersect D, this implies that x is in C intersect D. But this is equivalent to x in C and x in D. Thus, x is in D, which shows the contrapositive, or we can just say which concludes the proof. Because we have already told the reader that it suffices to prove that x is in D. And so we have already, with this phrase right here, it suffices to show that x is in D. It lets the reader know that once we show that x is in D, we are done. And that's what we have here. X is in D, and we can just conclude the proof right there. And so that finishes it off for this one. So let's look at now this example in the book. So the book does this via the contrapositive. I am going to do this directly. So here we have A, B, and C. They are real numbers. We have A is greater than B. And we want to prove that if AC is less than or equal to B times C, then C is less than or equal to 0. So let's do our scratch work. So we have, given, we have A is greater than B, we have AC is less than or equal to BC, and our goal is to show that C is less than or equal to 0. So what can we do? Well, here and for the material that we're covering now, we are assuming the laws from arithmetic that we have come to learn over the years. So one thing we could do is subtract the equation on both sides. So for example, if we have AC less than or equal to BC, subtracting on both sides by AC will give us 0 less than or equal to, actually let me do it the other way around, because essentially what I am doing is guiding myself with the fact that we want less than or equal to 0 for C. And so I'm going to subtract a BC over so that we can introduce a 0 on the right hand side. And so now we have AC minus BC less than or equal to 0. But that's the same as if we can now factor a C out. And that's the same as A minus B less than or equal to 0. So we have this. But now let's look at the A greater than B. We have that A is greater than B. If we now subtract B over, we end up getting that A minus B is greater than 0. In particular, a minus b is not 0. And the reason that this is important is that because it is not equal to 0, we can divide on both sides by a minus b. And so that will yield that c is less than or equal to 0. But notice that over here, we're also using an assumption about the inequalities. When we have an inequality and we divide by a positive number, it does not change the inequality. Had we divided by a negative quantity, then the inequality will flip. But in this case, we have c is less than or equal to 0. That's what we wanted to show. So we now have enough to do a proof for this. So let me just move this up. So now let's go through the formal argument. So proof. So that A, B, C. And now instead of saying real numbers, I'm just going to say they are in R. So this is acceptable, as I mentioned, mostly English, but we can use symbols here and there. So let A, B, C be in R. And suppose that A is greater than B, and A times C is less than or equal to B times C. Now, we want to guide the reader through the scratch work we did up here. But now, what we are going to do is write this in reverse. So, we saw that we can get from here to here once we know that A minus B is greater than 0. And so what I am going to do for the proof writing is mention this first, even though in our scratch work it came second. And so now, observe that A greater than B is equivalent to A minus B greater than 0. Thus, A minus B is a positive real number now. Next, we note that AC, and so now we go down to an equation. So we have A times C less than or equal to BC if and only if AC minus BC is less than or equal to 0, and then we explain what we did, subtracting both sides by BC. Now this, we can now factor a C out. We have A minus B less than or equal to 0, distributive property. And finally we have C is less than or equal to 0, dividing by A minus B since it is a positive real number. Oops, my handwriting is better over here, but that's real number. And we are done. We got the argument. And so we have our conclusion. In our book, this is done via the contrapositive. The contrapositive does give a faster argument for this one. Because if we apply the contrapositive, and I'm just going to sketch out the argument here. Please refer to the book for the formal write-up. But here we have C is less than or equal to 0. If we look at the contrapositive, then we negate this. This is C is greater than or equal to 0. Implies AC is greater than or equal to BC. And so the contrapositive is C greater than or equal to 0 implies that AC is greater than or equal to BC. But now, because we are assuming that A is greater than B, we can go ahead, multiply both sides by C, which is greater than or equal to 0, which tells us that this here will be AC greater than or equal to B times C, because there is the possibility that C could be 0, in which case we will have 0 on both sides, hence that inequality. And that's it. The proof is done. So the contrapositive gives a 1-2 step of showing this, whereas directly we had to take into account a couple of things with inequalities, but we still got the proof. And so that's one aspect for this coming homework, which as you do questions here, you want to ask, should we do the contrapositive? Should we do it directly? If you work with others, you could have some of you do direct proof, some of you attempt a contrapositive, and see the pros and cons of approaching one result via contrapositive versus direct. And what you'll see is that sometimes contrapositive does give an easier proof, sometimes direct gives an easier proof. In some cases, we just can't do a proof directly or via the contrapositive, and so there's the other approach we will have. And in our next lesson, we will introduce the method of proof by contradiction as well as the method of mathematical induction, and that will give us more tools for proving results in mathematics.